Khushbu, and in this video we are going to learn simulating values from different discrete distributions. So the first thing we come to is the uniform discrete distribution, right? And then there will be functions for all the other discrete distributions for simulating values from them. Okay, so there is one method which you can use while simulating values from discrete uniform distribution, and then there is one which you can use for all the other distributions with some changes, and that will be the second thing we come to. All right, so the first thing, let's say we are rolling a die, and the die is fair and has 6 sides. All right, so the possible outcomes will be stored in D and those outcomes will be the numbers 1 to 6, right? So this is how D looks. It has 1, 2, 3, 4, 5 and 6 as values, right? So now let's say we want to throw this die 100 times, okay, and we want to record all the outcomes that have been received by us in each of the 100 times. Okay, so there is this function called sample, right? So the sample function works as in to create a sample of different outcomes or values, right? So let's say we have D as the sample values, that is we have the values as 1 to 6 as numbers which we want to create as in a size of 100. So we want these 6 numbers to be repeated randomly and worked out 100 times, and another argument we use here is called replace. So if in case we wouldn't have asked R to replace the values, it would have used 1 only once, 2 only once, 3 only once, and so on. So the maximum length of the vector that we are requiring here would have been only 6, because these values wouldn't be allowed to be replaced, right? So here we ask R to let the values be replaced, right? So as you can see, the first argument is the values that we want to be created as a sample, right? So that is the first argument, the data. The second is the size of the vector that we want to create. So we want 100 simulations, right? And the last thing where we say we want replace as true, so that is where the values could be replaced, right? So there are 3 ways. First of all, you can write the argument names all together, and remember that if you write the argument names, you don't have to follow this order. You could write replace first and then write size, okay? But in case, like the third case, you are ignoring the names of the arguments altogether, you will need to follow the order of arguments that they should go in. So the first one has to be the data, the second one has to be the size, and the third one has to be the value for replace, okay? So you could even follow the second method where you could just write the size without the name of the argument and then give the name of the argument for replace. You can basically use all these 3 methods interchangeably. So in case you are not going to remember the order of putting anything through, use the first method. If not, if you're going to stick to the order, you could very well go with the third method. There is no difference made over here. Only thing that you will notice here is that the values that have been created here, the simulations that we have received, are not the same in all the 3 cases, right? So you can see the first case gives us the value 424666, right? The second one gives 656422, and the third one gives 514512, right? So the difference here is that every time the simulations are created very randomly. There is no particular pattern as to how R is going to do, and so there is not going to be consistency every time you run this particular simulation function or any other simulation function. So for us to have a consistent answer, there is something known as setting the seed value. You will come across this in a lot of questions later where you are asked to set the seed value to some particular number, okay? So the function to set the seed value is called set.seed, and within the brackets you specify any numeric quantity. It can range from 1 digit to n digits, okay? Doesn't matter. Only thing, if you want the same simulations to come later again, you just have to set the seeding value to be the same number, okay? So for now, let's say we have set the seed value to 77 and this is created, okay? So you can see how does S look right now. This is what has been created, right? So let us set the seed value again to 77 and run the previous function over here. Okay, so as you can see for S and for the other sample function that we have run over here, the values are completely the same. So basically this tells R, the set seed tells R to run the simulations in one particular order, which is represented by the number that you specify inside the brackets, and hence you don't get various answers every time you run the same simulation function. Okay, so now as you can see, we are going to be working with S and not the one previously we used. So S is our quantity here. And now let's say we want to sort the this S vector, all the values under the S vector in a table form, like a frequency table. You can use the table function where you specify S in the brackets, and as you can see here, it has the output in the form of a table. So 1 has appeared 15 times, 2 has appeared 18 times, 3 has appeared 18 times, and so on. Alright, so this is how you summarize it into a frequency table using the table function. And you can plot a histogram of the data that you have just simulated. So obviously the function to create a histogram is called hist. And we'll go to the arguments that are required inside. The first one has to be the data. So inside the hist argument, we have S. And as you can see, this is the histogram that is created. But you can see there is no difference between the bars created over here. There is no gap. But for rest all the bars, there has been a gap. So there is obviously some problem here. So we can actually ask R to keep a definite number of breaks that we want. So let's now say I want the breaks to be 6. I want 6 breaks. Okay, so that is the argument that you use here. And when you run that, you can see there is a continuous histogram without any gaps with 6 breaks. Okay. So now while you can see as you will read off the values just from the histogram and not the console over here, you can see that the values between 1 and 2 has appeared these many times. 2 and 3 has appeared these many times, which is not true, right? Because 1 has appeared this many times, 2 has appeared these many times, right? So for that, we can specify the breaks argument in a different form. We can ask the breaks to start from a point and range them till a point. So we start from 0.5, that is we want 1 to be in the middle, 2 to be in the middle, 3 to be in the middle, and so on. Okay, so we can start the breaks at 0.5 and end them at 6.5. So when you do that, you can see that in the middle the value of x-axis on 1 has appeared, and this basically says 1 has appeared 15 times, and then 2 has appeared something between 15 to 20, that was 18 times. 3 has again appeared for 18 times, 4 has appeared for 14 times, and so on. Okay, so this is how you make the histogram very obvious. You can use the breaks argument in this particular format, right? So now let's go to empirical probabilities. So what do we mean by empirical? Empirical basically refers to the fact that has already happened in the past, right? So if we would calculate the probabilities using the p binom or d binom function or any p or d functions, we can say those are the expected probabilities, right? But let's say we have a data over here and we just want to see, according to this data, what is the probability of any number then occurring? Okay, so those probabilities that we calculate on the basis of the data over here is basically the meaning for empirical probabilities, right? So let's see what is the probability of the number being the die roll landing up for a value that is less than equal to 4. Okay, so we use the length argument. We know what the length argument does. It counts the number of the places that has been occupied in the vector, right? And we use the indexing function. Okay, so we want the length of S where the value in S is less than equal to 4, right? We have come across indexing as well earlier. Okay, and then obviously we divide it by the total length of S, that is the total number of values that have appeared in S, that is 100, right? So when you do that, you get a value of 0.65. So the probability for the S to be less than equal to 4 is 0.65. Similarly, for S to be equal to 3, we used a double equal to symbol over here, which basically says that S has to be exactly equal to 3. And we use the same length and the indexing types. When you run that, you can see the probability comes to 0.18. Now in order to calculate for probability greater than 2, you can use the greater than symbol to specify the S values that you want. And when you want to select the values that are less than 2 or greater than 2, you can use the straight line, that is the straight vertical line symbol that is available on our keyboard to specify that you want the values to be this or that. Okay, so you use that. And similarly, we know to change this to and, we just use the ampersand symbol. Okay, so this is how you calculate the empirical probabilities, right? So now let's go to empirical movements. So naturally, we have a data set and we have a lot of ready-made inbuilt functions that we can use to calculate empirical movements. So for the mean, obviously we use the mean function. For median, we use median. For variance, we could either use the first principles, that is the formula for variance, and define it here by taking the s minus the mean of s, raise it to 2 and divide it by the n minus 1, right? That is the length of s minus 1. So we could either do that, or there is an inbuilt function called variance available, which gives exactly the same answer. Okay. Similarly, we could take the square root of this, or we can directly use the SD function, that is the standard deviation, and calculate the standard deviation for the same, right? And for the skewness, there is no inbuilt function, so you'll have to use your first principles. So you take the cube of s minus the mean of s, summate it, and divide it by the length of s, that is divided by n. Okay, we are giving it the name of skew over here, and when you run skew, this is what the value comes to. Okay, and finally, to find the coefficient of skewness, you divide the skewness by standard deviation raised to 3 or variance raised to 1.5. Okay, so this was about calculating the empirical movements. Okay, now we are going to go to another R script just to make sure that these values are not read off the way we have done in this particular R script. I'm going to erase my global environment, the graphs that I've created, and even my console, just so it is a little neater. Okay, and now I'm going to go to the other R script that I have created here. Okay, so now let's come to how do we simulate values from other distributions rather than just the uniform discrete distribution. Okay, so here we are going to take the example of the binomial distribution only, but remember the same methods and the same applications can be brought into use for other distributions like negative binomial, hypergeometric, Poisson, or geometric, all of them, right? So now let's come to this. Okay, so let's say a die is rolled 12 times and the number of sixes is modeled with the binomial distribution as parameters with 12 and 1 by 6, that is n is equal to 12 because the dice has been rolled 12 times, and the 6 to be appeared has the probability of 1 by 6, right, because it is a fair die. And we are now going to simulate possible outcomes of this experiment. We could use sample functions to do this from the scratch, right? The sample function that we use with another argument called prob, that stands for probability, right? So let's say 0 stands for the values of all the die rolls other than 6. Okay, so if say 1, 2, 3 or 5 appeared on the die, the outcome that we want to be displayed is 0, and if 6 appears, we want it to be 1. Okay, so we are just converting this into a binary situation. So my data is going to be the concatenated function of 0 and 1, right? I want 12 outcomes, so I'm going to set the size to be 12. I'm going to allow the replacement, right, because they can appear multiple times, so I'm going to say true. And when I say probability within the concatenate function, I write the probabilities for each of these happening respectively. So for 0 occurring, the probability is 5 by 6, right, collectively, because the probabilities for anything less than 6 appearing is 5 by 6, right? And for 6 to appear, that is our outcome to be 1, the probability is 1 by 6. Okay, so if say I had 3 or 4 values, I would need the exact same number of probabilities over here, which should summate to 1. Okay, otherwise there would be an error. This is one way how you can actually make this thing. Okay, and when you use the sum function around this particular sample function, it is just going to summate the values of 6s that have appeared, and so we get the total number of 6s that appeared. Okay, So because zeros sum to 1 and 1 adds up to 2, we should have got 2. But as we talked, we don't have a seed value over here. So a different simulation is going to be created every single time. And in this one particular outcome, there was only once that 6 appeared. So the summation comes to 1. Otherwise, it would have come to 2 for this upper outcome. Okay. We definitely know this is the longer way to do it because there's an inbuilt function for simulating values from all the defined distributions. Okay, so first of all, what we do is we set up n and p values, that are the parameters. So n is 12 and p is 1/6, and of course the inbuilt function is called r binom. Okay, for binomial distribution. Similarly, for Poisson it is r poise, for geometric it is r geom, for negative binomial it is r n binom, and for hyper it is r hyper. Okay, and we set the first argument to be the size of the vector that we want to be created. So 100, we want 100 outcomes that we can analyze. Okay, so we want 100 as the size, that is the first argument. The second argument is going to be n, and the third to be p. So basically these have to be in the order of the parameters that we have discussed earlier. So like for this is the same order we use for p binom or d binom functions, right? So that particular order has to be followed over here. Only thing that changes is the function's name, and the first one will be the size of the function that we want to create. Okay, so when you run that, you see these 100 outcomes have come that can be got by rolling the die. Okay, so here you can see there is no zeros and ones. These are basically the values that could have been created, right? So 2 could appear, 3 could appear, 4 could appear, and so on. So now let's set the seed value to be 31 and then run this thing so that we get consistent answers. And when you have done that, this is what the S looks like. This is what the sample space looks like. Okay, you can summarize it into a table, right? You can form a histogram over here. And again the same problem with the bars, so you can specify the breaks and you can start it from -0.5 and go till 12.5. So this is what it creates, right? Now these are the frequencies that have come to, right? These are the frequencies that the simulating function brought us to. We can definitely compare them with the frequencies that we would otherwise expect. There could be biases, right? Because the sample space is not very big where we can actually assume that this will be it, this will be exactly the format that is consistent with expected values, right? So what you can do is, first of all, you can set the x values to be 0 to 12, because we are going to plot a line over this particular graph where we can see how exactly the frequencies match with the expected outcomes. So we set the x values to be 0 to 12 and we use the lines function where our first argument is going to be the x values which are 0 to 12. The second one is going to be the d binom function for all the x values, and we multiply it with 100 because we want 100 outcomes like that, right? So d binom function basically gives the probability of any particular value occurring. So right, so for 3 to be occurring, the x value for 3, it is going to give the probability for that, right? And we are going to multiply it with 100 so that we have proper frequencies over here, right? We are going to use the type as O, that is overplotted, and we want a blue colored line, so we use the color argument as blue. Now as you can see over here, the line that appeared, that is the expected frequencies, and the histogram in the back is actually the frequencies that have empirically occurred, the actual frequencies, and these are the expected ones. So you can see there are some differences, right? So expected frequency for 0 to be occurred was less and more zeros have occurred. Similarly for 1, the frequency expected was more and less number of times 1 has occurred. For 2, definitely the expected frequency was very low, but they have occurred too many times, and so on. You can read off the frequencies over here. So we can see post the value of 6, the frequencies have very much settled down to 0 for both expected and actual ones, right? So now let's go to empirical probabilities. Okay, so the empirical probabilities, what you can do, as this is a table, you can do is you can use the table function and you can divide it by the total length of table. What it is going to do is for each of these values it is going to read this off and divide it by the total frequency. For the second one it is going to do the same, and so for the third and fourth and the rest of them. So when you do that, you come to a table where these are the x values and these are the px values. Okay, this particular form of the functions can bring you to this outcome. Okay, so now let's compare it with the actual probabilities. We are going to round the probabilities down to 2 decimal places. Okay, round is the function which you use around the d binom function or any other function where the first argument is the values that you want to round down to, and the second argument is the number of decimal places you want to round them down to. Okay, just to be able to compare it nicely, we are going to round them down to 2 decimal places, right? Because these occur in 2 decimal places only. So we use the d binom function, right? Because the expected frequency is what we are interested in. The first argument is going to be the x values, that is 0 to 12, and n and p are the parameters that are consistent, right? So as you can see, the probability, the empirical probability for 0 was 0.13, whereas the expected is 0.11. The empirical probability for 1 was 0.25 and the expected should be 0.27. For 2 was 0.37 and the expected was 0.3, and so on. It falls pretty much off to 0 after a point. Okay. Similarly, we'll calculate the empirical probability for the values less than equal to 2. So we use the length functions and do that, and we compare it with the p binom function where the value is 2. That is basically for all the values which are less than equal to 2, we calculate the expected probability. So the empirical probability was 0.75 and the expected is 0.677, right? For greater than 4, we do the same thing. Just for the p binom function, we call lower as false, so it is going to calculate for all the values greater than 4, or we could just not use the lower argument and subtract the first 3 arguments from 1, right? It would have got us to the same answer. We have discussed this earlier. Okay, so now let's go to empirical moments. Just like we did before, we can use all the previously used functions to calculate empirical moments, and also we can compare them with the actual or the expected values. Okay, so the mean of S, that is going to give the empirical mean, which is 1.82. But if we use the formulas for the binomial distribution, we can multiply n and p and get the expected mean, right, which comes to 2. So there is a little discrepancy over here. Similarly, we can calculate the median of S, and we can use the Q binom function, set the quantile to be 0.5 and see the median, which again comes to 2. So the median is the same, right? Same goes for the interquartile range. We can use the quantile function to calculate the 75th quantile and the 25th quantile. Okay, these are the inbuilt functions available. Or we could use the Q binom function to calculate the expected quantiles and subtract them to get the interquartile range. Okay. Same goes for the variance. You can calculate the variance using the variance function for empirical moments, and we can multiply n with p and 1 minus p to get the expected variance over here. Okay. Similarly, for skewness, you use the whole formula. You calculate the coefficient of skewness, and we can compare it with the expected values using this particular form of the formula. This is something that you have come across earlier. Okay, so you see there are some discrepancies over here as well. Right, so now let's go to trends. We can even recognize the underlying trends in the data that we have simulated over here, or any other data. For example, if that was the data that was imported and not just simulated, we can recognize the underlying trends. Okay, so now we are going to do it with the movements. So the movement here we are going to consider is mean. You can do it with every other movement, say for variance, for standard deviation, for skewness, for all of these. Okay, for any order of movement, here we are going to be dealing with mean, right? So let's say we are going to set the seed value to 31 and we are going to simulate 2500 outcomes using the R binom function. Okay, so S now has been redefined. There are 2500 outcomes now, right? And the first thing we do here is we create an average vector, okay, where we use the rep function where 0 has to be repeated 2500 times. So this is a blank vector of zeros that we are creating, okay. So when you do that, let's see how does this look. These are all the zeros. They have been repeated 2500 times, okay. And what you read here is basically the maximum print values has been reached, so 1500 entries have been omitted, so it's okay. Our the data in the background has all these already till 2500 values, but just here they have been omitted just while printing them into the console, okay. So now what we do is we create a for loop to calculate the mean for the first value, then for the first two values, then for the first three values, then for the first four values, and so on till we reach all the 2500 values, okay. So the means that are created, what we would otherwise expect for unbiased data is that in the long run the mean settles down to the expected mean, right? For large data, for large samples, the mean should be the same as the expected mean, or any other movement should be same as the expected movement, right? That is what we expect. So we are going to basically increase our sample size by 1 point every time we run the for loop, and see if the mean has occurred to settle down in the long run, okay. So for setting up the for loop, this is the format. So the for loop of course starts with for, and it is followed by round brackets where we write for I in 1 to 2500. This basically says that I is going to take the value of 1 in the first convolution, then 2 in the second, then 3 in the third convolution, and so on till the value of I reaches 2500. So basically this for loop is going to run itself 2500 times. So whatever we define inside this for loop is going to be run 2500 times, okay. And we are going to use the value of R inside this for loop. In case there are for loops where you do not use the value of I, it is also fine. It basically just says that the for loop is going to be run these many number of times. So even if you said it starts from 2 and goes till 2501, it basically is going to take the value of 2 first, then 3, then 4, and it will go on till 2501 times, okay. So that basically means the loop again will be run 2500 times, but the difference here will be the value of I will start from 2 instead of 1, okay. So this makes no sense by changing the values over here. Make sure that unless it is very necessary, you start your values in the for loop from 1 and go ahead till the value that you require, simply without meddling with the values, okay. Setting up a for loop is very important. It is going to come very handy later as well, so pay attention. So for the indexed value of I, so that is, let's say we are just talking about the first convolution, okay. So in the first convolution, what is this particular thing going to do? So in the average vector, in the first convolution, the first element is going to be selected, okay. So this one particular element is going to be selected over here in the first convolution, where we are going to redefine it to be the mean of the S, mean of the values in the S vector that we created, right? In the X vector, where it is going to calculate the mean for the values starting from the first position to the ith position. So in the first convolution, it is just going to calculate the mean for all the values that range from the first position to the first position. In the second convolution, the second value of the average vector is going to be selected, and it is going to be redefined to the mean of the values of S in the first position till the second position, and so on and so forth. So every time the consecutive value of the average vector is going to be selected, and it is going to be redefined as the mean of the S vector from the first value till that particular position that you have selected, okay. So we know that on the 100th convolution, the mean are going to be of the first 100 values of the S vector. In say the 1000th convolution, the mean is going to be the mean of the values of the first 1000 values of the S vector, and so on. It is basically going to increase your sample size from 1, go till a lot larger sample size and reach 2500 altogether. Okay, so you can see that as and when you increase your sample size, the means will be changing obviously, and then we are going to compare it with the expected means, just to check if the means has settled down to the expected means in the longer run. Okay, so now we can plot the trend of the average. Okay, so first of all what we do is we define the x values as 1 to 2500 naturally, and we use the plot function to plot x on the x-axis and the average from 1 to 2500 on the y-axis, right? You could have just ignored this square bracket and used the average argument, average vector as the argument. It would have done the same thing. So you can see here that these are the averages as and when the sample size has increased from 0 to 500 to 1000 to 1500 to 2000 and then finally to 2500, right? So you can see the trend in the changes of the averages over here. Okay, and we are going to add a horizontal line at the mean of 2. Why? Because n into p was coming to 2, right? That is the expected mean that we are expecting in the longer run. So we want a straight line starting from here, from the point 2 on the y-axis, running throughout the graph for us to compare if these values are properly conforming to the expected values. Okay, so the function we use here is called AB line. So AB line function has these all arguments. The first one is h is equal to 2. That is, we want the position to be on the y-axis as 2, right? The color we call as red, so we want a red line. The LTY stands for line type, and the value of 2, the line type of 2 basically stands for the dashed line. For say another value, for say 3, there would have been another type of line. For 4, there would have been another type of line. For 0 and 1, there would have been another type of line. Okay, so you can go to the help page and see all the values for the LTY function that creates different sorts of lines. Okay, and the LWD, that is the length, that is the line width argument. We discussed this earlier. We can meddle with this and change the thickness, that is the width of the line. Okay, so when you run this, there is this one horizontal line plotted on the graph where the value on the y-axis is 2 and it is red in color and it is a dotted line. And from reading of the graph, you can say in the long run the average is pretty much confined to the expected averages, right? So this was it. This was all that you need as a conceptual understanding. Remember that just not for the binomial distribution but for all the other discrete distributions as well, all these things can be run. All that you need to do is stick to the formats of the other distributions. All right, so you can now refer to the R scripts that have been provided to you, where all the other distributions as well as these concepts have been cleared very nicely. They are quite self-explanatory, and you are expected to learn the formats and the way the other distributions except for binomial and uniform work. Alright, so you can go there now and solve those. Also, it is better now if you start practicing the sums that have been provided to you. Okay, the solutions to them are also provided, right? The answers are also provided, so you can see where you stand. This is pretty much that you need to understand now, and you are good to go by solving and tackling problems by yourself. Alright, this is it for the video. Thank you. See you again later.